In the vastness of space, among billions of stars, lie worlds whose existence we are only beginning to surmise. Over 5,000 exoplanets have already been discovered, orbiting their stars and revealing their secrets through the light they receive. But what about those that remain in the shadows? Do planets exist that are devoid of starlight, wandering alone in eternal night? Imagine a world where the sun never rises, where only cold and darkness reign. Such planets indeed exist. They might be exiles, ejected from their home star systems as a result of cosmic collisions. Or perhaps they never knew the warmth of a star, born in isolation in the darkest corners of the galaxy. In 2011, astronomers made a groundbreaking discovery, reporting the existence of a new class of planets, dark, isolated objects comparable in mass to Jupiter. These planets drifted alone through space, unbound by the gravity of any star. Scientists concluded that such interstellar wanderers must be quite common, as a single study managed to detect 10 such objects at once. Imagine how difficult it is to find these dark worlds against the black backdrop of space. How did these planets end up alone? Several theories exist. Perhaps gravitational perturbations caused by passing stars disrupted the stability of their home planetary systems. As a result, planets could have been ejected beyond the star's influence or, conversely, moved too close and been destroyed. Another reason is the death of the host star. A powerful supernova explosion can send a planet on an interstellar journey at immense speed. However, the most probable scenario is the chaos prevalent during the early stages of star system formation. According to current understanding, not all planets survive into an era of stability. Some collide with each other, forming larger bodies. Others, due to gravitational disturbances, lose angular momentum and approach their star. In this cosmic struggle between larger and smaller planets, the smaller worlds are often ejected into unstable orbits or beyond the star's gravitational influence, becoming free-floating planets. Interestingly, a similar fate might have befallen a planet in our own solar system. According to one extended version of the NICE model, which describes the dynamic evolution of the solar system, we once had not 4, but 5 giant planets. Approximately 4 billion years ago, one of them, similar in mass to Uranus or Neptune, was ejected from the solar system as a result of Jupiter's migration closer to the Sun. Scientists have long suspected that the modern orbits of the planets cannot be explained without accounting for their past movements. For example, Uranus and Neptune could not have formed where they are now, as the disk of gas and dust at the edge of the solar system was too sparse. It is likely that the planets were initially closer to each other, and then spread out into wider orbits as the protoplanetary disk dissipated. The NICE model, developed in 2005, describes how gas planets, interacting with planetesimals, gradually moved into wider orbits, while Jupiter, conversely, moved inward. Then, an orbital resonance between Jupiter and Saturn increased their orbital eccentricities, which led to the outward scattering of Uranus and Neptune to the outer reaches of the system. There, the planets scattered the remaining planetesimals, forming the Kuiper belt and the Oort cloud. However, this model was not perfect. In 2011, a team of scientists led by David Nesvorny conducted a series of computer simulations to determine what conditions were necessary for the formation of stable orbits for the solar system's planets. To the researchers' surprise, only 10 out of 6,000 simulations resulted in all 4 planets surviving. In most cases, Uranus or Neptune left the solar system due to gravitational interactions. Scientists tried to avoid this by increasing the number of planetesimals in the disk to slow the escape of one of the planets, but this did not help. The best results were obtained only under the condition of a 5th planet existing between the orbits of Saturn and Uranus. It was this planet, ultimately, that was ejected from the solar system as a result of planetary migration. In 2015, a group of researchers decided to test the hypothesis of a 5th planet in the solar system. They created a computer model to determine how the gravitational interaction between Jupiter, Saturn, and a hypothetical planet would affect the movement of these gas giants' moons. The simulation results showed that if Saturn had indeed ejected a 5th planet from the system, it would have led to the destabilization of Iapetus' orbit, one of its moons. At the same time, Callisto, Jupiter's moon, would have maintained its orbit. This suggested that Jupiter might have been the one to eject the ice giant beyond the solar system. Such a 5-planet NICE model also explains why Jupiter, while moving inward into the solar system, did not disrupt the orbits of the terrestrial planets. Astronomers know of systems where gas giants migrated too close to their stars, turning into so-called hot Jupiters. Perhaps the gravitational influence of the hypothetical ice giant helped protect the inner planets of our system from chaos. If this 5th giant truly exists, then it is likely one of the countless rogue planets wandering through space. However, not all scientists are convinced that all interstellar planets resulted from gravitational ejection from their parent stars. Perhaps some of these planets formed far from stars, similar to how stars themselves are born. In giant cold molecular clouds, clumps of matter can contract under their own gravity, initiating thermonuclear reactions and forming stars. But clouds come in various sizes and masses, and some are quite small. They can separate from their parent cloud and evolve independently. In 2013, a team of scientists studied the Rosette Nebula using various radio and infrared telescopes. Researchers discovered that the Rosette Nebula contains over 100 tiny clouds known as globules. Compared to typical gas and dust clouds, globules are relatively small. Their diameter is only 50 times the distance between the Sun and Neptune. These structures also have a small mass for molecular clouds, up to 13 Jupiter masses. Scientists carefully measured the main characteristics of the globules, as well as their speed relative to the environment. It turned out that the globules are very dense and compact, and many of them have dense cores. This indicates that they are contracting under their own gravity and forming planetary mass objects that will move freely in space. The most massive of them can initiate thermonuclear fusion, but not of hydrogen like ordinary stars, but of its isotope, deuterium. In such a case, these would not quite be planets, but also not quite stars, but brown dwarfs, objects occupying an intermediate position between stars and planets. Astronomers found that the globules are moving at a speed of about 80,000 kilometers per hour out of the nebula. Perhaps the intense radiation from young and bright stars caused them to separate from the gas pillars and move outward at such high speeds. Stellar radiation pressure in nebulae could have scattered millions of globules throughout the Milky Way, creating free-floating planets. There may be so many of them that some scientists consider this process the primary source of interstellar planets in space. By various estimates, there may be even more free-floating planets in the Milky Way than stars. The upcoming Nancy Grace Roman Space Telescope and the ground-based Vera C. Rubin Observatory should provide more accurate data and significantly improve our understanding of interstellar planets. But how exactly will they do this, given that planets that emit almost no light and do not orbit stars cannot be detected by traditional methods? The phenomenon known as gravitational microlensing comes to the rescue. Any object with mass warps spacetime around it and causes light to deviate from a straight path. By measuring the degree of light deviation, scientists can determine the mass of the object creating the warp. Using this effect, astronomers have measured the masses of galaxies, their clusters, and even clumps of dark matter, which manifests itself only gravitationally. Gravitational lensing is also suitable for studying less massive objects, such as free-floating planets. When a planet happens to pass in front of a distant bright star from an observer's perspective, its gravity deflects and focuses the star's light. As a result, the observer sees a temporary increase in the star's brightness. By measuring the degree of brightness change, astronomers can calculate the mass of the object that caused the gravitational lensing. Thus, even an invisible planet reveals itself for a short period through microlensing. In October 2020, scientists managed to discover the first interstellar planet comparable in mass to Earth. Astronomers at the University of Warsaw recorded an amplification of starlight in the densest part of the Milky Way. This event lasted about 42 minutes, and the analysis of the planet's mass showed it was similar to Earth. It turned out to be even less massive than our planet, and was not gravitationally bound to any star. This was probably the last time astronomers had the opportunity to observe this celestial body, as the microlensing effect by its nature, is a unique and unrepeatable event. Returning to this planet for further research is no longer possible. The only thing left is to patiently wait for a new microlensing event from another planet, which could occur anywhere in the sky at any time. However, there is a workaround that allows for the direct detection of free-floating planets. They need to be observed while still hot, soon after their formation. They still retain enough heat, which they radiate into space. Of course, this radiation will be significantly weaker than starlight, as the peak emission of sun-like stars is in the visible range, while young interstellar planets primarily emit in the infrared range. Nevertheless, modern telescopes have sufficient sensitivity to capture even such faint light sources. In 2021, a team of astronomers discovered a cluster consisting of at least 70 Jupiter-mass free-floating planets. All of them were found in an active star-forming region in the constellations Scorpius and Ophiuchus. The team of scientists had to analyze archival observational data obtained from various telescopes, including the European Southern Observatory's Very Large Telescope and the European Space Agency's Gaia spacecraft. As a result, detailed sky maps were created in the visible and infrared ranges, covering a total of 20 years of observations. The researchers then identified faint objects that moved in a way that indicated their belonging to the star group in the constellation, rather than to distant background stars. Ultimately, the team managed to discover between 70 and 170 free-floating planets, which is currently the largest sample of such objects. Due to the inability to precisely measure the mass of the planets, the researchers relied solely on their brightness. Consequently, many of these objects could be brown dwarfs, whose mass exceeds 13 Jupiter masses. This explains the imprecise estimate of the number of planets, from 70 to 170. The authors of the study suggest that most of these planets formed as a result of gravitational collapse, but at least 10% of them must have originated as part of a star system. As for the rest of the galaxy, the authors believe that the number of rogue planets should be roughly equal to the number of planets that initially existed in isolation. Interestingly, conditions on the surface of interstellar planets are not necessarily unfavorable for the existence of life. Paradoxically, there are several scenarios in which even these worlds could harbor simple life forms or even more complex organisms. As early as 1999, scientists hypothesized that a hydrogen-rich atmosphere on an interstellar planet could prevent the loss of heat generated by the decay of radioactive elements. Since hydrogen in the atmosphere possesses greenhouse gas properties, it would absorb and retain heat, preventing it from radiating into space. The authors of the study claim that the surface temperature of such planets could be high enough for water to be in a liquid state. A later work, published in 2020, expands on this idea. Researchers conducted thousands of computer simulations to determine how long hydrogen atmospheres could retain heat on planets slightly more massive than Earth, i.e., so-called super-Earths. They found that the greenhouse effect could maintain moderate surface temperatures for billions of years. However, internal heating from radioactive elements is infinitesimally small compared to the heat received from the sun, so it remains unclear whether this heat is sufficient for life to originate on such planets. The probability of life significantly increases if, for example, a free-floating planet has its own sufficiently massive moon, as tidal forces could further heat it from within. Such systems appear to have already been observed. In 2014, the discovery of a candidate interstellar planet with a mass approximately 4 times that of Jupiter was announced, around which orbits a moon whose mass is half that of Earth. Computer modeling shows that almost half of rogue planets, if they are gas giants, could retain their moons, at least some of them. If we are talking about less massive rocky planets, their chances of retaining their moons are significantly lower, up to 5%. The authors of this study argue that, given the possibility of life on Europa or Enceladus, the moons of rogue planets also have a chance to be habitable. Furthermore, free-floating planets forming in isolation from a star could be surrounded by their own gas and dust disk, within which moons are born. At least one such system is known, OTS-44, a candidate free-floating planet or brown dwarf, appears to be surrounded by a disk with a mass of at least 10 Earth masses and possibly forming its own mini-solar system. Thus, the discovery of traces of life, or at least confirmation that the moons of our gas giants can support conditions for life, will only heighten interest in free-floating planets.